The universe is a vast and terrifying place, filled with worlds that seem straight out of the darkest corners of science fiction. Beyond the safety of our planet, there are places so hostile, so bizarre, that they defy all logic and understanding. From planets with crushing gravity and toxic atmospheres to worlds where it rains glass or metal, the horrors of space are as endless as they are unimaginable. In this video, we're venturing into the most horrifying planets in the cosmos. These are the places that push the boundaries of what we think is possible. Alien worlds where survival is not just unlikely, but utterly impossible. So brace yourself as we take a journey to the most terrifying corners of the galaxy, where the universe reveals its most nightmarish wonders. Gliese 581c, located just 20 light-years from Earth in the constellation Libra, was once heralded as a potential haven for life, a planet that could resemble our own. But closer analysis revealed a stark and horrifying reality. Rather than being a second Earth, Gliese 581c is a world of extremes, locked in a perpetual struggle between fire and ice. The planet orbits a red dwarf star, Gliese 581, at a distance that initially seemed promising for habitability. However, its proximity to its star has resulted in tidal locking, a phenomenon where one side of the planet perpetually faces the star, while the other remains in eternal darkness. This creates a dramatic and deadly environment. The star-facing side of Gliese 581c is subjected to relentless radiation and blistering temperatures that soar well above 1,000 degrees, 537 degrees. Any matter exposed on this side would likely be incinerated instantly. The atmosphere, if it exists, would be a superheated, chaotic cauldron of gases. In stark contrast, the planet's dark side is a frozen wasteland. Shrouded in eternal night, this hemisphere endures unimaginably frigid temperatures, plummeting to levels where no known form of life could survive. Ice would form in layers thick enough to rival the great glaciers of Earth, assuming any moisture could exist under such conditions. The lack of sunlight renders this side a barren, icy tomb. Between these two extremes lies a narrow twilight zone where day and night meet, a band of perpetual dusk. While this region might appear at first glance to be a potential refuge, it is anything but hospitable. The extreme temperature gradient between the scorching day side and the frozen night side drives catastrophic winds across the planet. These winds, fueled by the violent thermal contrasts, can reach thousands of miles per hour, scouring the surface with unrelenting force. Any atmosphere that might exist would be a churning storm, where hurricanes rage continuously, fueled by the energy disparity between the two hemispheres. The red dwarf star itself adds to the planet's inhospitable conditions. Red dwarfs are known for their violent stellar flares, emitting bursts of radiation that can strip away planetary atmospheres and bombard any surface with lethal levels of energy. For a planet as close as Gliese 581c, these flares would pose a constant threat, further diminishing any chance of habitability. Gliese 581c serves as a stark reminder that the cosmos is filled with worlds vastly different from Earth. While its position in the so-called habitable zone initially sparked hope, the reality of its environment underscores the complexity of planetary systems and the challenges of finding truly Earth-like conditions elsewhere in the universe. This planet, with its dichotomy of fire and ice, demonstrates how even the most promising candidates can turn out to be alien and hostile landscapes. It is a brutal world, unsuited for life as we know it, and a testament to the unforgiving nature of the cosmos. HD 2009-458b, also known as Osiris, is a gas giant exoplanet located approximately 150 light-years away in the Pegasus constellation. It is a planet that defies the typical understanding of planetary stability, existing under extreme conditions that push the limits of astrophysical phenomena. Orbiting its parent star, HD 29458, at an incredibly close distance, Osiris completes one orbit in just 3.5 Earth days. This proximity places it in a category known as hot Jupiters, gas giants subjected to the intense heat and radiation of their stars. Osiris is remarkable for its atmosphere, which is being stripped away by the unrelenting stellar radiation. This process creates a massive tail of gas trailing behind the planet, resembling a comet's tail and stretching across thousands of miles into space. The planet's temperatures reach an astonishing 3,600 degrees, 2,000 degrees, far hotter than any environment on Earth. At these temperatures, the hydrogen and other elements in its atmosphere are heated to such an extent that they escape the planet's gravitational pull. This phenomenon of atmospheric escape has made Osiris one of the first exoplanets where such a process was directly observed, offering scientists an invaluable opportunity to study atmospheric dynamics under extreme conditions. One of the most astonishing aspects of HD 209458b is its bizarre weather. It rains molten iron droplets in its atmosphere, a phenomenon that sounds like something out of science fiction. However, these iron droplets never reach any solid surface, as the planet is a gas giant with no defined ground. Instead, the droplets vaporize as they fall through the superheated layers of the atmosphere, adding to the intense and hostile conditions. This process of atmospheric stripping is driven by the extreme ultraviolet radiation from the planet's star. The high-energy photons ionize hydrogen atoms in the atmosphere, accelerating their escape into space. This phenomenon has allowed scientists to detect specific elements in Osiris's tail, including hydrogen, carbon, and oxygen. The discovery has provided critical insights into the composition of exoplanetary atmospheres and the long-term evolution of planets in such hostile orbits. The loss of atmosphere has led researchers to refer to Osiris as the evaporating planet. Over time, it is estimated that Osiris could lose a significant portion of its gaseous envelope, but its mass, comparable to that of Jupiter, ensures that the process will take billions of years to significantly alter the planet. Nonetheless, it is a vivid example of how extreme conditions can radically reshape a planet's structure and environment. Osiris has become a cornerstone in the study of exoplanets. Its discovery and subsequent observations mark significant milestones in the field of astrophysics. It was the first exoplanet detected through the transit method, where astronomers observe the dimming of a star's light as a planet passes in front of it. This method has since become a standard technique for discovering thousands of exoplanets. Furthermore, HD 209458b was also the first exoplanet where astronomers directly measured atmospheric escape and identified specific chemical elements in its atmosphere. The study of Osiris has profound implications for understanding planetary evolution and the diversity of planetary systems in the universe. It raises questions about how planets form and adapt to their environments, particularly those that develop in close proximity to their stars. Observations of HD 29458b and other hot Jupiters have challenged existing models of planetary formation and migration, providing new perspectives on how planets behave under extreme gravitational and radiative forces. Osiris stands as a vivid example of the extremes that exist in the universe. It is a planet in constant transformation, sculpted by the harsh environment of its stellar neighborhood. For scientists and space enthusiasts alike, it represents a glimpse into the fascinating and often violent processes that shape worlds beyond our solar system. Kepler-70b is one of the most extreme and hostile worlds ever discovered in our universe. This planet, located in the Kepler-70 system, orbits its parent star at an astonishingly close distance of just 0.01 astronomical units, AU, a mere fraction of the Earth-Sun distance. At this proximity, the planet completes one full orbit in just 5.6 hours. This breakneck orbital period places it among the fastest orbiting planets ever observed. The environment of Kepler-70b is nothing short of hellish. Its surface temperature reaches an unimaginable 12,000 degrees Fahrenheit, 6,600 degrees Celsius, making it hotter than many stars, including our own sun's surface, which averages around 10,000 degrees Celsius, 5,500 degrees. Such blistering heat ensures that no form of life as we know it could ever survive there, and the very materials that make up the planet are pushed to their limits. Kepler-70b is believed to be the remnant core of a former gas giant, a planet that once resembled Jupiter. The intense conditions it now endures are the result of a catastrophic transformation during its host star's red giant phase. Billions of years ago, its star swelled to hundreds of times its current size, engulfing and obliterating the outer layers of Kepler-70b. What remains today is thought to be the stripped, molten core of the once massive gas giant. This planet's close orbit around its star is also a significant factor in its extreme heat. At 0.01 AU, the energy it receives from its star is far greater than what Mercury experiences in our solar system. The intense radiation and gravitational forces likely play a role in maintaining the planet's molten state. Any solid matter on the surface, if it exists at all, would rapidly vaporize in the extreme temperatures. Kepler 70b is also notable for its potential interactions with a neighboring planet, Kepler 70c. These two planets are separated by only 240,000 kilometers, a distance closer than the Moon is to Earth. Such proximity may lead to extreme gravitational effects, contributing further to the volatile conditions of the system. Studying Kepler 70b offers valuable insights into planetary evolution, especially the final stages of gas giants that come too close to their stars. It also demonstrates the extremes that planets can endure, surviving events as catastrophic as a star's red giant phase. However, Kepler 70b is a stark reminder of the harsh and unforgiving realities that exist beyond our solar system. It showcases the immense power of stellar processes and the dramatic fates that can befall planets orbiting too close to their parent stars. This planet, with its record-breaking heat and rapid orbit, stands as a testament to the diversity of worlds in the universe and the extremes to which they can be pushed. Kepler 70b is not just a scientific curiosity, but a window into the violent and transformative processes that shape the cosmos. HD 189733b, located approximately 64 light-years away in the constellation Vulpecula, is a planet that challenges our understanding of extraterrestrial weather. At first glance, this gas giant might appear deceptively beautiful, shining with an alluring sapphire blue hue. However, beneath its striking exterior lies an environment of unparalleled ferocity and danger, a world that defies human imagination. This planet belongs to a class of exoplanets known as hot Jupiters. These massive gaseous planets orbit extremely close to their host stars, resulting in intense surface conditions. HD 189733b completes its orbit around its parent stars in just over 2 days. This proximity to the star subjects the planet to intense radiation and heat, creating an environment that is both hostile and extreme. The stunning blue color of HD 189733b is caused by the scattering of light by silicate particles in its atmosphere. While this appearance might remind us of Earth's oceans, any similarity ends there. The planet's atmosphere is a maelstrom of chaos, with winds that reach staggering speeds of up to 400 miles per hour. For comparison, these winds are more than 7 times the speed of sound on Earth and are powerful enough to hurl objects at unimaginable velocities. If you were somehow able to stand on the surface of HD 189733b, the winds alone would shred anything in their path. But the true horror of HD 189733b lies in its unique and deadly precipitation. The planet experiences rainstorms, but not of water. These storms consist of molten glass. Silicate particles suspended in the atmosphere condense under the extreme heat and form molten droplets. These droplets solidify into shards of glass as they fall through the cooler layers of the atmosphere, only to be caught in the planet's violent winds. The combination of supersonic winds and raining glass creates a phenomenon unlike anything found in our solar system. The molten glass is whipped around the planet at incredible speeds, effectively turning HD 189733b into a cosmic blender. Any object, or hypothetically any spacecraft, exposed to these conditions would be subjected to relentless bombardment by sharp, high-speed fragments of glass. The energy and force involved are unimaginable, making HD 189733b one of the most inhospitable planets ever discovered. The temperature on the planet further adds to its hostile nature, with daytime temperatures soaring to around 1,700 degrees Fahrenheit, 930 degrees Celsius. The atmosphere is a furnace of superheated gases. This heat is responsible for the formation of the silicate clouds that give rise to the glass rainstorms. At these temperatures, not only is survival impossible, but the very materials of most spacecraft would melt or disintegrate. HD 189733b also provides valuable insights into the nature of exoplanets and their atmospheric dynamics. The planet has been extensively studied, using telescopes like the Hubble Space Telescope and the Spitzer Space Telescope. Observations have revealed the unique chemical composition of its atmosphere, including the presence of methane, carbon monoxide, and the silicates responsible for its deadly rain. These findings help scientists understand how extreme conditions can shape planetary atmospheres and offer clues about the diversity of planets in the universe. Despite its terrifying conditions, HD 18973 plays a critical role in advancing our understanding of exoplanets. It serves as a reminder that the cosmos is filled with worlds far stranger and more extreme than anything we might have imagined. While the idea of molten glass storms and supersonic winds may seem like something out of science fiction, they are a reality on this distant planet, a reality that underscores the vast and often violent diversity of worlds beyond our solar system. WASP-12b is one of the most fascinating and horrifying planets ever discovered. Located approximately 870 light-years from Earth in the constellation Auriga, this gas giant is a prime example of how extreme and destructive the universe can be. Unlike the planets in our solar system, WASP-12b exists under conditions so severe that its very existence is a constant battle against annihilation. This exoplanet orbits its host star, WASP-12, at an incredibly close distance, completing a full orbit in just over a single Earth day. This proximity places it in a category known as hot Jupiters, gas giants that orbit their stars at blisteringly close ranges. WASP-12b is tidally locked, meaning one side of the planet perpetually faces its star, while the other remains in constant darkness. This results in extreme temperature differences between the two hemispheres. The day side experiences temperatures soaring to nearly 2,500 degrees Celsius, hot enough to vaporize metals and break apart molecules in its atmosphere. The immense gravitational forces exerted by its host star have distorted the shape of WASP-12b. Instead of being spherical like most planets, it has been stretched into an elongated, egg-like shape. This deformation occurs because the planet's gaseous outer layers are being pulled toward the star, creating immense tidal forces. The star's gravity is so powerful that it has begun stripping material from the planet's outer atmosphere. This process, known as mass transfer, is occurring at an extraordinary rate. An estimated 189 quadrillion tons of material are siphoned off from the planet every year. This steady loss of mass has turned WASP-12b into what scientists call a cannibalized planet. Over time, its atmosphere is being funneled into an accretion disk surrounding the star. This disk, a swirling ring of gas and dust, is a telltale sign of the planet's ongoing destruction. Observations have confirmed that the planet is losing significant amounts of hydrogen and helium, the primary components of its atmosphere, to its star. The extreme environment of WASP-12b offers a grim reminder of the delicate balance required for a planet to maintain its stability. Its proximity to its star not only subjects it to gravitational stripping, but also exposes it to intense radiation. The ultraviolet radiation from WASP-12 ionizes the planet's atmospheric particles, further accelerating their escape into space. This relentless process suggests that WASP-12b is on a path to total destruction. Astronomers estimate that the planet may only survive for another 10 million years, a mere blink in cosmic time, before it is completely consumed. The study of WASP-12b provides valuable insights into the dynamics of planetary systems and the forces that shape them. It serves as a natural laboratory for understanding tidal interactions, atmospheric escape, and the life cycles of gas giants. The data gathered from this planet has helped scientists refine models of planetary evolution and better understand the harsh conditions that can arise in close-orbiting systems. Despite its hostile environment, WASP-12b is a crucial piece in the puzzle of exoplanetary science. Its extreme nature challenges our understanding of planetary formation and survival. For now, it remains a vivid example of how the universe can create and destroy worlds in ways that defy imagination. WASP-12b's story is one of inevitable demise, a stark reminder of the forces at play in the cosmos, and a testament to the delicate balance required for planetary existence. In the vast and unyielding cosmos, some celestial bodies stand out not for their beauty or promise, but for their sheer hostility and inhospitality to life as we know it. One such planet is PSR B125712b, an unassuming yet horrifying world orbiting a pulsar, a type of neutron star that spins at an incredible speed and emits powerful beams of electromagnetic radiation. This planet, which is part of a system located approximately 2,300 light-years from Earth in the constellation Virgo, exists in one of the most brutal environments imaginable. A pulsar is the remnant of a massive star that has undergone a supernova explosion, collapsing into a dense, rapidly spinning object no larger than a city. Pulsars emit beams of radiation that sweep through space like cosmic lighthouses. PSR B107+12b, the innermost of 3 planets in its system, is locked in a relentless and deadly embrace with this pulsar, which serves as its parent star. The radiation emitted by the pulsar is extreme and incessant, bombarding the planet with intense gamma rays, X-rays, and other forms of high-energy particles. The conditions on PSR B1257+12b are nothing short of catastrophic. Any atmosphere the planet may have once possessed has likely been stripped away by the pulsar's relentless radiation. Without an atmosphere to shield it, the surface of PSR B12b is directly exposed to this high-energy bombardment. This makes the planet an irradiated wasteland where temperatures fluctuate wildly and the surface is likely scorched, barren, and devoid of any chemical processes conducive to life. The environment is further compounded by the gravitational forces at play. The pulsar's immense gravitational pull keeps the planet locked in a tight orbit, subjecting it to tidal forces that may cause its crust to crack and shift. This geological activity, combined with the constant radiation, ensures that PSR B157+12b remains an utterly inhospitable world. Even the planet's core, if it exists, would be influenced by the pulsar's intense magnetic fields, potentially creating a chaotic internal structure. From a scientific perspective, PSR B1257+12b is fascinating, as it was among the first exoplanets discovered in 1992. Its presence challenges our understanding of planetary formation and survival in extreme conditions. The existence of planets around pulsars was unexpected, as the violent supernova explosion that creates a pulsar would typically obliterate any nearby planets. The mere survival of PSR B127+12b suggests it either formed after the pulsar's birth or somehow endured the cataclysmic forces of the supernova. However, from the standpoint of habitability, PSR B127+12b is a definitive no-go. Life as we understand it cannot emerge or sustain itself in such a hostile environment. The radiation levels alone are lethal to any known biological molecules, rendering even the most resilient extremophiles incapable of survival. Additionally, without an atmosphere or stable temperature range, the planet offers no refuge from the incessant cosmic onslaught. In the grand scheme of the universe, PSR B17112b serves as a stark reminder of the diversity and harshness of planetary environments. While Earth thrives under the protective warmth of the Sun, PSR B127.12b is locked in an eternal struggle for existence against the relentless forces of its pulsar host. It stands as a testament to the extremes of planetary survival, an uninhabitable relic of cosmic evolution in one of the most unforgiving regions of space. This desolate world, though unwelcoming to life, offers invaluable insights into the processes that shape planets and their interactions with their stellar hosts. It challenges scientists to rethink the boundaries of planetary science and to consider the resilience of matter in the universe's harshest corners. PSR B12557b is not just a planet, it is a chilling example of nature's raw power, where survival is impossible and existence is defined by the relentless fury of a pulsar's radiation. Among the most astonishing and terrifying worlds discovered in the universe is TRES 2b, a gas giant unlike anything seen in our solar system. Known as the darkest planet ever observed, this alien world challenges our understanding of planetary science and offers a chilling glimpse into the extreme diversity of exoplanets. TRES-2b orbits a star located approximately 750 light-years from Earth in the constellation of Draco. It was first discovered in 2006 as part of the Transatlantic Exoplanet Survey. Initially, it appeared to be a standard gas giant similar to Jupiter. However, closer observation revealed a startling and unique characteristic. TRES-2b reflects less than 1% of the light that hits it. For perspective, this makes it darker than coal, black acrylic paint, or even the blackest volcanic rock. Its albedo, a measure of how much light a surface reflects, is the lowest ever recorded for a planet. The planet's darkness is so extreme that it essentially appears as a void in space. Even when viewed directly, it absorbs nearly all the light from its parent star, giving it an appearance of being enveloped in a black abyss. The only faint light detectable from the planet comes from a thermal glow caused by its intensely hot atmosphere. This eerie red glow is a result of the planet's temperature, which exceeds 1,800 degrees Fahrenheit, about 1,000 degrees Celsius. Despite its darkness, TRES-2b's heat radiates a dim, ghostly light, similar to the faint glow of embers in a dying fire. Scientists have been intrigued by the mechanisms behind TRES-2b's near-total light absorption. Unlike reflective planets like Venus, which is covered in bright clouds of sulfuric acid, TRES-2b lacks reflective clouds or surfaces. Instead, its atmosphere appears to be dominated by light-absorbing chemicals, such as vaporized sodium and potassium, as well as titanium oxide. These substances are exceptionally efficient at trapping light, contributing to the planet's haunting blackness. Additionally, TRES-2b's proximity to its star, it orbits closer than Mercury does to the Sun, means that the intense heat prevents the formation of reflective clouds or ice that might brighten its surface. TRES-2b is classified as a hot Jupiter, a type of gas giant that orbits very close to its host star. Such planets are known for their high temperatures and unique atmospheric properties. But even among this group, TRES-2b stands out. Its incredible darkness is a mystery that defies easy explanation. For example, while other hot Jupiters often display bright reflections due to their atmospheres, TRES-2b seems to have evolved in a way that absorbs nearly all incoming radiation. One of the most unsettling aspects of TRES-2b is the way it distorts expectations of what a planet should look like. In our solar system, even the darkest planets, such as Uranus or Neptune, reflect at least a small portion of sunlight, creating visible features or colors. TRES-2b offers no such familiarity. Its appearance as a pitch-black void with only the faintest red thermal outline is completely alien. This unsettling visual profile makes it a standout among the thousands of exoplanets discovered to date. Another puzzling feature of TRES-2b is how it maintains its temperature despite its darkness. A typical dark object in space would absorb light and heat up, but TRES-2b appears to have reached a thermal equilibrium where its emitted heat matches the energy it absorbs. This balance is still not fully understood, particularly given the lack of reflective materials in its atmosphere. Some scientists hypothesize that the intense gravity of TRES-2b, combined with its rapid orbital speed, could create internal heat through tidal forces, contributing to its high temperature. TRES-2b challenges the notion of what constitutes a planet. Unlike Earth or Mars, which are solid and visually dynamic, TRES-2b offers no comforting landscapes, no familiar patterns of weather or climate, and no features that resemble anything we have encountered before. It is a reminder that the universe is full of worlds beyond our comprehension, each governed by its own unique set of physical laws and conditions. Despite its terrifying appearance, TRES-2b serves an important role in advancing our understanding of planetary science. Its extreme properties provide a valuable laboratory for studying atmospheric chemistry, heat transfer, and the effects of close stellar proximity on planetary systems. Researchers continue to observe TRES-2b using advanced telescopes and instruments, hoping to uncover more about its composition and behavior. Each new piece of data brings us closer to understanding not only this specific planet, but also the broader variety of worlds that exist in the universe. 55 Cancri is a planet that defies ordinary imagination. Located 41 light-years away in the constellation Cancer, this exoplanet is classified as a super-Earth. With a diameter about twice that of Earth and nearly 8 times its mass, It represents an entirely different kind of world, one forged in extremes. What sets 55 Cancri apart from other exoplanets is its composition and the violent conditions it endures. This planet is composed primarily of carbon, a feature that suggests it has undergone processes vastly different from those of Earth. Under the crushing pressure and intense heat that exist on 55 Cancri, this carbon is believed to have been transformed into diamond. In essence, much of the planet's surface and interior could be a giant reservoir of crystalline carbon, what we would call diamond on Earth. This has earned it the nickname the Diamond Planet. However, the conditions on 55 Cancri are so extreme that the prospect of mining or even observing this diamond trove up close is beyond current human technology. The surface of 55 Cancri experiences temperatures that can soar to 4,400 to 2,400 Joule. Such extreme heat is primarily due to its proximity to its parent star, 55 Cancri, a sun-like star located much closer to the planet than Mercury is to our sun. This close orbit causes 55 Cancri to complete one revolution in just 18 hours, exposing it to relentless stellar radiation. The planet is tidally locked, meaning one side perpetually faces the star, baking under unrelenting heat, while the far side remains in eternal darkness. Adding to the hostility of this world is its atmosphere, which appears to contain high levels of vaporized rock and metallic gases. Observations suggest the presence of silicate particles in the air, and under the extreme temperatures, liquid silicon may even rain down on the surface. This creates a planet-wide phenomenon where molten droplets condense in the searing atmosphere and fall back onto the surface like fairy precipitation, a scenario utterly foreign to earthly conditions. Scientists believe that 55 Cancri has no stable surface as we understand it. Instead, the immense heat and pressure could mean a landscape of molten rock and liquid metals. On the scorching day side, the atmosphere likely glows due to thermal radiation, making the planet shine like a furnace in the darkness of space. The night side, by contrast, might be cooler, but not cool enough to allow for solid ground. The stark contrast between its two hemispheres results in massive atmospheric currents, creating turbulent winds that sweep across the planet at unimaginable speeds. The intense heat and high levels of carbon suggest that 55 Cancri may have originally formed further away from its star before migrating inward. This inward migration likely altered its chemical makeup and subjected it to conditions that intensified the transformation of its carbon into diamond. Such a process highlights the dynamic and often violent evolution of planetary systems, emphasizing how different worlds can be compared to the Earth we know. Despite its uninhabitable conditions, 55 Cancri has captured the imagination of scientists and the public alike. It challenges our understanding of planetary formation and composition, as it provides evidence of worlds vastly different from our own. The discovery of this diamond furnace raises questions about the diversity of planets in the universe and the extreme conditions they can endure. While the sparkling diamonds on 55 Cancri might seem appealing, this is a planet that is anything but welcoming. It is a testament to the universe's ability to create beauty in the most hostile of environments, even if that beauty is forever out of reach. GJ-1214b is one of the most extraordinary and unsettling exoplanets discovered to date. Located approximately 40 light-years away in the constellation Ophiuchus, this alien world is often referred to as a water world. It is a super-Earth, meaning it has a mass and size greater than Earth's, but less than that of the gas giants. What makes this planet so horrifying and fascinating is its unique composition. It is made almost entirely of water, and the conditions on its surface and within its atmosphere are extreme in every imaginable way. The most striking feature of GJ-1214b is its dense, thick atmosphere. This atmosphere traps immense amounts of heat, creating a suffocating greenhouse effect. The temperatures on this planet are estimated to range between 200 and 500 degrees Celsius, 392 to 932 degrees Fahrenheit, turning it into a superheated, high-pressure environment. This is not the gentle warmth of a tropical Earth ocean. It is an unrelenting, searing furnace, wrapped in layers of dense, vapor-rich gases. The atmospheric composition of GJ-1214b adds another layer of intrigue. Observations suggest that its atmosphere is dominated by water vapor, but not in the way we experience it on Earth. The high pressures and temperatures force the water into a bizarre state. The lower atmosphere is a steamy, suffocating expanse where water exists as a dense, supercritical fluid, a phase of matter that is neither a liquid nor a gas but shares properties of both. This supercritical water has a density similar to liquid but flows like gas, creating an environment that defies ordinary physical laws. Beneath this turbulent atmosphere, the planet's crushing gravity plays a critical role in shaping its internal structure. The immense gravitational forces compress the water into exotic forms. One of the most peculiar phenomena on GJ12 and 14b is the likely presence of hot ice. This is not ice as we know it, but an exotic phase of water that forms under extreme pressure. On Earth, ice forms at low temperatures, but under the immense pressure inside GJ12 and 14b, water molecules are forced into crystalline structures even at extremely high temperatures. These forms of ice, such as Ice 7 or Ice X, are solid but exist only in the most extreme conditions and are completely alien to anything we encounter on Earth. The planet's surface, or what might qualify as a surface, is equally enigmatic. If there is a solid core beneath the layers of water and hot ice, it is likely surrounded by vast oceans of supercritical water. However, these oceans would not be serene or hospitable. They would be subjected to unimaginable pressures, rendering them fundamentally different from any oceanic body on Earth. The boundary between the supercritical water and the solid ice below is thought to be a chaotic zone where the laws of physics seem almost surreal. GJ12104b's density measurements provide critical clues about its composition. Scientists believe that up to 75% of the planet's mass could be water, a stark contrast to Earth, where water makes up only about 0.05% of the planet's mass. This dominance of water, combined with the extreme conditions, raises profound questions about how such a planet could have formed and evolved. Did it begin as a rocky planet like Earth and later accumulate vast amounts of water? Or did it form in a region of its star system rich in ice, which later melted and transformed under its star's heat? The star GJ1214b orbits a red dwarf known as GJ1214, is another factor that shapes the planet's horrifying nature. Red dwarfs are cooler and smaller than our Sun, but they are also prone to violent stellar activity. Frequent flares and bursts of radiation bombard GJ1214b, further complicating its atmospheric dynamics. This relentless radiation likely strips away lighter molecules, leaving behind a thick, water-rich envelope. The planet's close proximity to its star also means it is tidally locked, with one side perpetually facing the star and the other in constant darkness. This creates extreme temperature gradients and volatile weather patterns, contributing to the chaotic and hostile environment. The study of GJ1214b offers unique insights into the diversity of planets in the universe. While it is unlikely that such an extreme environment could support life as we know it, its discovery broadens our understanding of what planets can be like. The idea of a world dominated by water, yet so alien in its conditions, challenges preconceptions about habitability and planetary formation. It also highlights the incredible adaptability of water as a substance, capable of existing in forms and phases far beyond what is familiar to us on Earth. GJ12 and 14b is a testament to the vast and often terrifying variety of planets in the cosmos. It is a world where water, so essential to life on Earth, becomes a source of chaos and inhospitable extremes. Kepler-10b is a planet that defies the imagination. Located roughly 560 light-years away from Earth in the constellation Draco, this rocky world has earned its place in scientific history as the first confirmed terrestrial exoplanet discovered by NASA's Kepler Space Telescope. But what makes Kepler-10b truly extraordinary is not just its status as a milestone in planetary discovery, it's the extreme conditions under which this planet exists. Kepler-10b is a rocky planet with a surface that has been pushed to unimaginable extremes. Orbiting its host star at a distance of just 1/20th of Mercury's orbit around the Sun, Kepler-10b completes a full revolution in less than a single Earth day, a mere 20 hours. This proximity to its star subjects it to intense gravitational forces and, more dramatically, scorching temperatures that make the planet's surface a global ocean of molten lava. The dayside temperature of Kepler-10b exceeds 2,500 degrees Fahrenheit, about 1,370 degrees Celsius, a heat so intense that it reduces the planet's crust to a churning, molten sea. This unrelenting heat leaves no room for stability on the surface. The lava flows and shifts constantly, driven by the extreme energy pouring down from the star it orbits. The brightness of the star would dominate the sky from the planet's surface, if any observer could survive to witness it, which they could not. Any atmosphere that Kepler-10b may have once possessed has long since been stripped away by the intense radiation and solar wind from its host star. Without an atmosphere to buffer or regulate temperatures, the day side of the planet is an exposed inferno, while the night side, likely shielded from direct starlight, might experience slightly cooler conditions. However, the molten nature of the surface likely facilitates heat redistribution, meaning the night side could still maintain extremely high temperatures. There is no respite from the extreme heat anywhere on the planet. Kepler-10b's composition is believed to be similar to that of Earth, with a rocky mantle and metallic core. However, the extreme proximity to its star and the relentless heat have caused a transformation that is unlike anything seen in our solar system. The crust has melted entirely, creating a landscape that more closely resembles the primordial Earth during its early molten phase, billions of years ago. On Kepler-10b, however, this molten state is not a temporary phase. It is the planet's permanent condition. The gravitational pull of Kepler-10b's host star, combined with the planet's close orbit, may also play a role in shaping its unusual environment. Tidal forces are likely immense, causing internal friction that generates additional heat within the planet. This tidal heating, combined with the radiation from its star, ensures that Kepler-10b remains a searing world of molten rock. The discovery of Kepler-10b has provided scientists with a glimpse into the extremes of planetary evolution. Its proximity to its star places it in a category known as hot super-Earths, or lava planets, a class of exoplanets where surface conditions are dominated by extreme temperatures. These planets challenge our understanding of planetary formation and survival in such hostile environments. Kepler-10b, for example, must have formed further away from its star, where conditions were cooler, and later migrated inward to its current hellish orbit. Despite its hostile environment, Kepler-10b is a valuable subject of study. Observing such extreme planets allows astronomers to test models of planetary formation, structure, and behavior under conditions vastly different from those of Earth. It also offers insight into the diversity of planetary systems in the universe, highlighting just how varied and extraordinary planets beyond our solar system can be. Kepler-10b is not a world where life as we know it could exist. Its surface is too hostile, its environment too extreme, yet it serves as a stark reminder of the incredible diversity of planets that populate our galaxy. From molten lava worlds like Kepler-10b to frozen ice giants and everything in between, the universe is a place of endless extremes and boundless wonder. Horrifying is one of the most extreme exoplanets discovered, a world that defies comprehension with its hostile and destructive environment. Orbiting its parent star at a blistering distance of just 2.5 million kilometers, Horrifying experiences an unimaginable onslaught of stellar radiation. This radiation is so intense that it transforms the very nature of the planet's surface, creating conditions that can only be described as apocalyptic. Horrifying was discovered by the CoRoT, Convection, Rotation, and Planetary Transits space mission, which was designed to find exoplanets and study stellar interiors. This planet is located approximately 480 light-years away in the constellation Monoceros. It is classified as a rocky super-Earth, roughly 1.6 times the size of Earth and nearly 5 times its mass. However, any resemblance to Earth ends with its rocky composition. What sets CoRoT-7b apart is its extreme proximity to its star, a G-type main sequence star similar to our Sun, but slightly smaller and cooler. CoRoT-7b completes an orbit around its star in just 20.4 hours, meaning a year on this planet lasts less than a single Earth day. This close orbit places Corot 7b in a state of perpetual hellfire, with surface temperatures on the star-facing side reaching as high as 2,500 Celsius, 4,500 Celsius. These temperatures are hot enough to melt rock, creating seas of molten lava on the planet's surface. The intense heat doesn't just melt the rock, it vaporizes it. The extreme temperatures cause the rocky surface to emit gases and particles, forming a thin atmosphere composed primarily of silicates, sodium, and other elements found in rock. This process is akin to a rocky evaporation, where the planet's crust and surface materials are slowly turned into a vapor. But the destruction doesn't end there. The vaporized rock in the atmosphere doesn't remain aloft forever. Due to the planet's gravity and cooling processes on the dark side of the planet, the vapor condenses into droplets and falls back to the surface as a form of rock rain. This cycle creates a continuous and horrific feedback loop. Rock is melted, vaporized, and then rains back down onto the planet's molten surface, perpetuating the destruction in an endless cycle. This rain of rocky particles is unlike anything we see on Earth. Instead of water droplets, the atmosphere of Corot 7b contains elements such as silicon dioxide, iron, and other metallic components. As these particles condense, they harden into sharp, glassy fragments or molten droplets that splash back onto the lava oceans, further fueling the planet's volatile environment. The atmosphere itself is likely transient, constantly being replenished by the ongoing vaporization of the planet's surface. Corot 7b's environment also poses questions about the planet's origin and future. Scientists believe that Corot 7b may have once been a much larger gas giant, similar to Neptune. Over time, its proximity to its star could have stripped away the outer layers of gas, leaving behind the rocky core we observe today. This theory highlights the devastating effects of stellar radiation on planetary bodies, offering insights into the evolution of planets in extreme environments. The planet's rapid orbit in extreme conditions also make it tidally locked, meaning one side perpetually faces the star while the other remains in constant darkness. The dark side of the planet is much cooler, although still far from hospitable. The sharp contrast between the scorching day side and the cooler night side likely creates intense winds, further contributing to the chaotic environment. Corot 7b is not just a planet, it is a testament to the destructive power of stars. Its existence challenges our understanding of planetary systems and underscores the diversity of worlds in our universe. While it is unlikely that Corot 7b could ever support life as we know it, studying such extreme worlds provides valuable data about the boundaries of planetary science and the potential for unusual phenomena in other star systems. In conclusion, Corot 7b is a world of perpetual destruction, where rock vaporizes, forms a thin atmosphere, and rains back down onto a molten surface in a nightmarish feedback loop. It represents one of the most extreme environments ever discovered, a place where the very fabric of the planet is constantly torn apart by the unrelenting radiation of its parent star. Through the lens of Corot 7b, we gain a deeper appreciation for the resilience of planets and the dynamic, often hostile nature of the cosmos. Celt 9b is a gas giant that redefines the limits of planetary extremes. Discovered in 2016, it orbits Celt 9, a star located about 670 light-years from Earth in the constellation Cygnus. What sets Celt 9b apart from all other planets is its incredible heat. This planet is the hottest ever discovered, with surface temperatures soaring beyond 7,800 degrees, 4,300 degrees Celsius on its day side. The sheer intensity of this environment challenges our understanding of how planets can form and survive in such hostile conditions. The key factor driving Celt 9b's extreme heat is the star it orbits. Celt 9 is an A-type star, meaning it is significantly hotter and more massive than our Sun. Its surface temperature exceeds 10,000 degrees, 5,500 C, making it one of the hottest stars known to host a planet. Celt 9b is locked in an extraordinarily close orbit, completing a full revolution around its star in just 1.5 Earth days. This proximity means that the planet is subject to unrelenting radiation, with its atmosphere perpetually blasted by intense ultraviolet and visible light. The extreme heat has profound effects on Kelt 9b's atmosphere. Temperatures on its dayside are so high that hydrogen molecules, typically the most abundant component of gas giant atmospheres, are ripped apart into individual atoms. This process, called molecular dissociation, is rarely observed in planetary atmospheres because it requires conditions far more extreme than those found in our solar system. As these hydrogen atoms are carried by strong winds to the planet's cooler night side, they recombine into molecules, only to be torn apart again when they circulate back to the day side. The intense radiation from Kelt 9 also causes the atmosphere to expand significantly, creating a kind of puffed-up effect. The planet's atmosphere is so swollen and extended that it leaks into space, forming a comet-like tail of evaporating gas. This phenomenon has led scientists to compare Kelt 9b to a planet on the verge of disintegration. Over time, the constant loss of atmospheric material may strip the planet down to its core, though such a process would likely take billions of years. Another extraordinary aspect of Kelt 9b is its classification as an ultra-hot Jupiter. While it shares similarities with the gas giants in our solar system, such as Jupiter and Saturn, Kelt 9b's environment is utterly alien. The heat and radiation have stripped its atmosphere of many of the features typically associated with gas giants. For example, molecules like water vapor and methane, which are abundant in Jupiter's atmosphere, cannot survive the blistering temperatures of Kelt 9b. Instead, the planet's atmosphere contains heavy elements like iron and titanium in vaporized form. These metals, normally found as solids or liquids on Earth, are present as gases due to the extreme heat. Kelt 9b's orbit is another unusual feature. It is tidally locked, meaning one side of the planet permanently faces its star, while the other remains in perpetual darkness. This results in a stark temperature contrast between the day and night sides, with the night side being thousands of degrees cooler. However, powerful atmospheric winds, driven by the temperature gradient, work to distribute heat around the planet. These winds can reach speeds of several kilometers per second, further emphasizing the chaotic and violent nature of the planet's environment. Despite its extreme conditions, Kelt 9b offers valuable insights into planetary science. It serves as a natural laboratory for studying how atmospheres behave under extreme radiation and temperature. Observations of the planet, often conducted using powerful space telescopes like Hubble and Spitzer, have revealed unique spectral signatures, helping astronomers identify the chemical composition of its atmosphere. These studies not only enhance our understanding of Kelt 9b, but also contribute to broader efforts to understand exoplanets as a whole. Kelt 9b challenges the boundaries of what we consider a planet. Its extreme conditions blur the line between planets and stars, particularly brown dwarfs, which are often described as failed stars. The intense heat and atmospheric loss make it a fascinating example of planetary evolution in action. By studying Kelt 9b, scientists can explore questions about the formation and survival of planets in extreme environments, shedding light on the diversity of worlds that exist in our universe. Kelt 9b is not just a record-breaking planet, it is a reminder of the incredible diversity and adaptability of planetary systems. Its existence expands our understanding of the types of environments that planets can inhabit and survive. While Kelt 9b may seem more like a celestial furnace than a planet, it is a vital piece of the puzzle in humanity's quest to understand the cosmos. LHS 3844b is a planet unlike any we would consider familiar or hospitable. Located roughly 48.6 light-years away from Earth, it orbits an M-dwarf star, the most common type of star in the universe. Despite its unassuming distance in cosmic terms, this exoplanet is one of the most extreme environments known to astronomers. Its defining feature? It is utterly barren and lifeless, a rocky world scorched by its proximity to its host star. This planet falls into the category of superheated rocky planets, a class of worlds that endure extreme conditions due to their size, composition, and location relative to their parent stars. LHS 3844b is slightly larger than Earth, with a radius about 1.3 times that of our planet. However, any similarities with Earth end there. Unlike our world, which is teeming with life thanks to its protective atmosphere, LHS 3844b has none. Its atmosphere, if it ever had one, has been stripped away, likely due to the relentless bombardment of radiation from its star combined with its close orbit. Without an atmosphere, LHS 3844b is entirely exposed to the harsh realities of space and the radiation from its star. This lack of atmospheric insulation causes extreme temperature variations between the planet's day side and night side. The day side is perpetually baked by the unyielding glare of its star, with surface temperatures reaching a staggering 400 degrees or 760 degrees. This is hot enough to melt many types of rock and create a surface environment akin to an open furnace. In contrast, the night side of LHS 3844b is locked in frigid darkness, with temperatures plummeting nearly to absolute zero. Without sunlight to provide warmth and with no atmosphere to redistribute heat, the night side becomes a frozen wasteland. This stark temperature dichotomy between the two hemispheres further highlights the planet's uninhabitable nature. One of the most intriguing aspects of LHS 3844b is its tidally locked orbit. This means one side of the planet always faces its star, bathing it in constant daylight, while the other side is perpetually turned away, engulfed in eternal night. This phenomenon is a common characteristic of planets that orbit very close to their stars. Tidally locked planets often experience these extreme temperature differences because the lack of rotation relative to their star prevents heat from being evenly distributed. The surface of LHS 3844b, as observed through data from telescopes such as NASA's Spitzer Space Telescope, reveals more details about its desolation. Scientists believe it is composed of basalt, a volcanic rock similar to the material found in Earth's oceanic crust. This suggests that the planet may have experienced volcanic activity in its past. However, any dynamic geological processes have long since ceased, leaving behind a static, lifeless landscape. The absence of an atmosphere on LHS 3844b has significant implications for its potential to harbor life. Atmospheres not only provide a shield from harmful stellar radiation, but also play a critical role in maintaining stable surface temperatures and enabling the chemical processes necessary for life. On LHS 3844b, the absence of this essential component makes the existence of even microbial life highly unlikely. Astronomers continue to study LHS 3844b to better understand its origins and the processes that shaped its current state. The planet's close proximity to its star likely played a role in the loss of its atmosphere. Stellar winds, streams of charged particles emitted by the star, combined with intense radiation, may have stripped away any gaseous envelope early in the planet's history. This process is not uncommon for planets orbiting M-dwarf stars, which are known for their volatile and energetic behavior during their early lifespans. The study of LHS 3844b also provides valuable insights into the diversity of planets in our galaxy. It serves as a stark reminder of how harsh and unforgiving many planetary environments can be. For every Earth-like world that might exist, there are likely countless others like LHS 3844b, worlds that are inhospitable, lifeless, and shaped by forces far beyond human control. While LHS 3844b may not be a candidate for colonization or even further exploration with current technology, it plays a critical role in advancing our understanding of planetary science. It offers a glimpse into the extreme conditions that can arise in the universe and challenges our notions of what a planet can be. For now, it stands as a haunting example of a dead land, silent, unyielding, and brutally indifferent to the existence of life. WASP 76b is a planet unlike anything we know on Earth, a world where the laws of physics and extreme conditions combine to create an environment that can only be described as otherworldly. Located about 640 light-years away in the constellation Pisces, this exoplanet has earned its reputation as one of the most horrifying planets discovered to date. Its most infamous feature? It rains iron. WASP 76b is classified as a hot Jupiter, a type of gas giant that orbits perilously close to its host star. Its orbit is so close that a year on WASP 76b lasts only 1.8 Earth days. This proximity exposes the planet to intense stellar radiation, resulting in surface temperatures on its star-facing side reaching an unimaginable 2400 Celsius 4352 degrees. At these temperatures, even metals like iron are vaporized. The extreme conditions on WASP-76b are further amplified by its tidally locked orbit. This means one side of the planet, the day side, always faces its star, while the other side, the night side, remains in perpetual darkness. The temperature difference between these two hemispheres drives ferocious winds, with speeds estimated to reach thousands of kilometers per hour. These winds serve as the planet's heat redistribution system, carrying vaporized materials from the searingly hot day side to the cooler night side. It is this dynamic system that gives rise to the phenomenon of iron rain. On the blazing day side, temperatures are high enough to vaporize iron, turning it into a gaseous state. The intense heat ensures that the iron remains suspended in the atmosphere as a vapor, mixing with other elements in this alien environment. However, as the winds transport this vapor to the night side, where temperatures drop to around 1,100 degrees, 2,132 degrees, the cooler conditions cause the iron vapor to condense. This process is analogous to water vapor condensing into rain on Earth, but with one critical difference. Instead of water, the precipitation on WASP-76b consists of molten iron droplets. These droplets fall in sheets, cascading down from the upper atmosphere in what can only be described as a metallic storm. The sheer intensity of such rain is difficult to imagine, but it is a direct consequence of the planet's unique atmospheric conditions. Adding to the planet's mystique is the discovery of asymmetric iron signatures in its atmosphere, detected by astronomers using advanced spectroscopy. This finding supports the idea that the iron vapor primarily condenses on the night side, creating a sort of cold trap where iron-rich precipitation occurs. However, due to the high temperatures on the night side, even this iron rain does not solidify. Instead, it likely remains molten as it reaches the planet's surface or lower atmospheric layers. The implications of such an environment are staggering. WASP-76b is not just a planet with extreme weather, it is a vivid example of how the universe can produce environments that challenge our understanding of physics and chemistry. The iron rain phenomenon highlights the complex interplay between temperature, atmospheric dynamics, and material properties in conditions far removed from those on Earth. Scientists studying WASP-76b aim to better understand how such planets form and evolve. The extreme nature of its environment provides a natural laboratory for exploring atmospheric processes under conditions that cannot be replicated on Earth. These studies not only deepen our knowledge of exoplanets, but also contribute to our understanding of planetary systems as a whole. Despite its horrifying conditions, WASP-76b remains a fascinating subject of study. It is a reminder of the vast diversity of worlds that exist in our galaxy and a testament to the power of science to uncover the secrets of the cosmos. For those seeking to understand the extremes of planetary science, WASP-76b stands as a shining and terrifying example of nature's ability to push boundaries. Gliese 436b, a planet orbiting a red dwarf star approximately 30 light-years away in the constellation Leo, is one of the most baffling and counterintuitive celestial bodies ever discovered. This Neptune-sized exoplanet has a characteristic that defies common sense and challenges the limits of our understanding of planetary physics. Despite scorching surface temperatures exceeding 800 degrees, around 440 degrees, much of the water on this planet exists in a solid state. This phenomenon creates what scientists describe as hot ice. The key to this paradox lies in the extreme gravitational forces exerted by Gliese 436b's massive size. The planet's gravity is strong enough to compress water into a solid form, even under the intense heat that would typically vaporize it. This state of matter, known as Ice 7, or superionic ice, is unlike the ice found on Earth. It forms under immense pressure and remains stable in conditions that would seem impossible to us. On Gliese 436b, this superionic ice exists deep within the planet, encased by a thin atmosphere rich in hydrogen and helium. To understand how this works, it is important to consider the environment on Gliese 436b. The planet orbits extremely close to its host star, completing a full orbit in just 2.6 Earth days. This close proximity subjects Gliese 436b to immense stellar radiation, which heats its outer atmosphere to extreme temperatures. The radiation causes some of the atmosphere to escape into space, forming a comet-like tail of gas trailing the planet. Despite this, the high pressure in the planet's interior prevents the water from evaporating completely, forcing it into its solid yet superheated form. The existence of hot ice on Gliese 436b demonstrates the incredible versatility of water as a substance. Under the right conditions, water can transition into exotic states that do not exist naturally on Earth. On Gliese 436b, the combination of extreme heat and pressure has created a planetary environment that defies conventional physics. Another fascinating aspect of Gliese 436b is its relatively low density compared to other planets of similar size. This suggests that a significant portion of its mass is composed of water or water-related compounds. Scientists theorize that the outer layer of the planet may consist of superheated steam or other volatile gases, while the interior is dominated by this exotic solid-state water. The interplay between these layers contributes to the planet's unique characteristics. The discovery of Gliese 436b has profound implications for our understanding of exoplanets and the potential diversity of planetary systems. It demonstrates that the conditions we consider extreme on Earth are just a small fraction of the possibilities in the universe. By studying planets like Gliese 436b, scientists can better understand how planets form and evolve under different conditions. Gliese 436b also raises intriguing questions about habitability and the potential for life in extreme environments. While the planet itself is far too hostile to support life as we know it, its study helps refine our search for habitable exoplanets. By exploring the wide range of planetary environments that exist, we can develop better models for identifying worlds where life might arise. In summary, Gliese 436b is a planet of contradictions. Its burning ice cube nature challenges our assumptions about what is possible in the universe. The discovery of this remarkable world is a testament to the ingenuity of modern astronomy and a reminder that the cosmos is far stranger and more complex than we can imagine. Through ongoing research, Gliese 436b continues to inspire curiosity and deepen our understanding of the universe's many mysteries. HD 106906b, a rogue giant located in a star system 336 light-years away in the constellation Crux, defies conventional planetary norms. This gas giant orbits its host star at an astonishing distance of 650 astronomical units, AU, where 1 AU equals the average distance between Earth and the Sun. To put this into perspective, this is more than 16 times the distance of Pluto from the Sun. Such an orbit places HD 106906b in an extraordinary category, far removed from the planetary configurations we typically observe. At this distance, HD 106906b resides in an icy, desolate region of space, far beyond the traditional boundaries of its star's gravitational influence. This separation has profound implications for its environment and its relationship with the rest of the star system. The planet is enveloped in perpetual cold, receiving an extremely faint glow from its host star. Its atmosphere likely consists of thick layers of hydrogen and helium, with trace amounts of other gases that have frozen under the extreme conditions. Without significant stellar warmth, the planet's surface is shrouded in darkness, offering a stark contrast to the vibrant and dynamic environments of planets closer to their stars. The orbital dynamics of HD 106906b raise intriguing questions. Such an extreme orbit suggests it may not have formed in its current location. Instead, scientists hypothesize that the planet was initially much closer to its host star, forming alongside other planetary bodies in the star system's protoplanetary disk. Over time, a series of gravitational interactions, possibly involving a passing star or the presence of another massive object within the system, could have flung HD 106906b into its current distant trajectory. This violent ejection would have left it in a precarious position, barely held within the star's gravitational grasp, making it one of the most isolated planets known to date. Adding to its mystery is the fact that HD 106906b appears to be relatively young in cosmic terms, estimated at only 13 million years old, an infant by planetary standards. Despite its distance, the planet's heat signature, a remnant from its formation, has allowed astronomers to detect and study it. Observations suggest it is several times the mass of Jupiter, classifying it as a gas giant. Its size and youthful warmth make it an exceptional candidate for studying the early stages of planetary evolution in extreme environments. The planet's extreme separation from its star raises important questions about planetary formation and stability. In most star systems, gravitational forces within the protoplanetary disk dictate that planets form within a relatively narrow range of distances. HD 106906b's current orbit lies well beyond the reach of these forces, suggesting either a dramatic migration or an alternative mechanism of planetary formation. One theory posits that HD 106906b might have formed in situ, far from the star, through a process resembling the formation of binary star systems, where material coalesces independently rather than within a shared disk. However, this hypothesis remains controversial, as the conditions for such formation are exceedingly rare. HD 106906b's existence also has broader implications for our understanding of rogue planets, bodies that wander through space without a host star. While HD 106906b remains loosely bound to its star, its extreme distance and isolation make it a borderline case, providing a unique glimpse into the dynamics of planetary systems and the factors that influence planetary retention versus ejection. It serves as a natural laboratory for exploring the processes that shape planetary orbits and the potential for planets to exist in the vast, frigid outskirts of star systems. Another fascinating aspect of HD 106906b's story is its potential parallels to hypothetical Planet 9 in our own solar system. Like HD 106906b, Planet 9 is theorized to exist far beyond the Kuiper Belt, exerting subtle gravitational influences without direct observation. By studying HD 106906b, astronomers hope to refine models of how massive planets can end up in such distant orbits and what observable signatures they might leave behind. Ultimately, HD 106906b challenges our understanding of what it means to be a planet. Its remote location, combined with its massive size and unusual history, defies the conventional models of planetary behavior. As researchers continue to study this enigmatic world, it may provide critical insights into the formation and evolution of planetary systems, offering a window into processes that were previously beyond our imagination. HD 106906b stands as a testament to the diversity and complexity of the cosmos, a reminder that the universe still holds countless secrets waiting to be uncovered. Proxima Centauri b, located approximately 4.2 light-years from Earth, is the closest known exoplanet in the habitable zone of another star. Orbiting Proxima Centauri, a red dwarf star in the Alpha Centauri system, this planet represents a tantalizing possibility in humanity's search for extraterrestrial life. However, this potential is overshadowed by significant challenges, making Proxima Centauri b an extraordinarily fragile cradle for life. The planet lies within the habitable zone, the orbital region around a star where conditions might allow for liquid water on a planet's surface. This positioning is one of the primary reasons Proxima Centauri b has garnered attention. Liquid water is a key ingredient for life as we know it, and the mere possibility of its existence on Proxima b has fueled scientific curiosity and speculation. Yet the conditions on this planet are far from idyllic. Proxima Centauri, the star that anchors this planet, is a red dwarf. Red dwarfs are the most common type of star in our galaxy, but they are far from stable or hospitable. These stars are known for their long lifespans and relatively low luminosity, but they are also notorious for their violent outbursts. Proxima Centauri in particular is highly active, frequently emitting powerful solar flares. These flares release enormous amounts of charged particles and radiation into space, creating a hostile environment for any planets in close proximity. Proxima Centauri b orbits its parent star at an extremely close distance, much closer than Mercury orbits the Sun in our solar system. This tight orbit places the planet well within the range of Proxima Centauri's intense flares. The energy released during these flares can strip away an atmosphere over time, a process known as atmospheric erosion. For a planet to support life, a stable atmosphere is crucial. It provides a buffer against harmful radiation, helps regulate surface temperatures, and retains essential gases like oxygen and carbon dioxide. On Proxima b, the constant bombardment from solar radiation makes it difficult for any atmosphere to remain intact over geological timescales. In addition to the risk of atmospheric loss, the planet is likely subject to intense radiation levels. Proxima Centauri emits significant amounts of X-rays and ultraviolet radiation, far more than our Sun does. Without a robust magnetic field to deflect this radiation, any surface life, or even potential subsurface life, on Proxima b would be exposed to lethal levels of radiation. While Earth's magnetic field provides a critical shield, there is no definitive evidence that Proxima b has a similar protective mechanism. Furthermore, the close orbit of Proxima Centauri b likely results in tidal locking, a phenomenon where one side of the planet always faces its star while the other remains in perpetual darkness. This creates extreme temperature contrasts, with one hemisphere baking under constant daylight and the other shrouded in eternal night. The habitable zone in such a scenario would be limited to a narrow band along the terminator, the region where day transitions to night. Even within this band, conditions would be highly variable and difficult for life to adapt to. Despite these challenges, the possibility of subsurface water or life remains a topic of intense research. Proxima Centauri b's rocky composition and potential for Earth-like mass make it conceivable that water, if present, could be protected beneath the surface. Subsurface oceans, shielded from the harsh radiation by layers of rock and ice, might offer a stable environment for microbial life. However, this remains purely speculative, as no direct evidence of water or life has yet been found on the planet. The discovery of Proxima Centauri b has also spurred interest in developing advanced technologies to explore nearby star systems. Projects like Breakthrough Starshot aim to send tiny, high-speed spacecraft to Proxima Centauri within a few decades, potentially allowing for direct observation of this enigmatic planet. Such missions could provide crucial data on its atmosphere, surface conditions, and potential habitability. Proxima Centauri b represents both a fragile hope and a harsh reality. While its proximity and location in the habitable zone make it an intriguing candidate for further study, the challenges posed by its environment are daunting. The planet serves as a reminder that habitability is not defined solely by a planet's position relative to its star, but also by a complex interplay of atmospheric, magnetic, and geological factors. HAT P7b, a planet located over 1,000 light-years away in the constellation Cygnus, is one of the most fascinating yet deadly exoplanets discovered. This gas giant is classified as a hot Jupiter due to its massive size and extreme proximity to its host star, HAT P7. While its physical characteristics may seem dazzling, they conceal an environment so hostile that it defies imagination. The most striking feature of HAT P7b lies in its atmosphere, which is laden with clouds composed of corundum, the mineral that forms sapphires and rubies. This unique chemical composition gives rise to an exotic and shimmering sky, potentially filled with glints of gem-like particles. Yet this beauty is overshadowed by the planet's harsh and chaotic nature. HAT P7b is tidally locked to its star, meaning one side of the planet perpetually faces the searing heat of its sun, while the other remains cloaked in eternal darkness. The day side of HAT P7b reaches temperatures of over 2,500 degrees, 4,500 degrees, making it an uninhabitable furnace. The intense heat causes the atmosphere on the day side to expand and rise before circulating to the cooler night side, creating massive temperature gradients. These gradients are the driving force behind the planet's violent weather. Storm systems on HAT P7b are unlike anything experienced on Earth. Observations suggest that these storms are dominated by winds that move at supersonic speeds, exceeding 5,400 miles per hour, 8,690 kilometers per hour. These winds tear through the atmosphere, transporting heat, gas, and the corundum-rich clouds across the planet. The powerful atmospheric currents create immense turbulence, resulting in storms that are not only vast in scale, but also unpredictable in their behavior. Adding to the chaos, the extreme heat on the day side causes elements like hydrogen and helium to become highly energized, contributing to the dynamic and volatile nature of the atmosphere. On the cooler night side, temperatures plummet dramatically, potentially condensing some elements out of the atmosphere and creating stark contrasts in weather patterns. It is theorized that as the corundum-rich clouds are carried from the day side to the night side, they may cool and crystallize, forming gem-like particles that rain down before being swept back into the raging storms. The sapphire and ruby-like clouds give HAT P7b a dazzling appearance when observed from afar. But up close, the environment is far from tranquil. Lightning storms, driven by the planet's extreme winds and temperature differences, may crackle through the atmosphere, adding another layer of danger. These electrical discharges are believed to be far more powerful than any lightning storms found on Earth, fueled by the abundance of charged particles in the planet's turbulent skies. HAT P7b's close orbit around its host star further exacerbates its violent nature. The planet completes an orbit in just 2.2 Earth days, meaning it is subjected to continuous and intense gravitational forces. These forces cause tidal heating, which may contribute to the extreme conditions observed. The proximity to its star also means that HAT P7b is constantly bombarded by stellar radiation, stripping away lighter elements in the upper atmosphere and possibly leaving behind heavier elements like corundum. The study of HAT P7b has provided valuable insights into the behavior of extreme exoplanetary atmospheres. Its unique characteristics challenge our understanding of planetary formation and weather dynamics. The discovery of gem-forming minerals in its atmosphere has opened up new questions about the chemical processes that occur under such extreme conditions. While it may be one of the most beautiful planets known, HAT P7b is also a reminder of the hostile and diverse environments that exist beyond our solar system. In conclusion, HAT P7b is a world of contradictions, stunning yet deadly, chaotic yet fascinating. Its sapphire and ruby-filled skies are a testament to the wonders of the universe, but its wild storms and unrelenting heat serve as a stark reminder of the dangers that lie beyond the comforts of our own planet. Scientists continue to study this extraordinary exoplanet to uncover its secrets, but for now, HAT P7b remains a dazzling enigma, a planet where beauty and destruction coexist on an unimaginable scale. OGL 2005 BLG 390LB is a planet that stands as a stark reminder of the universe's extremes. Located approximately 20,000 light-years away in the direction of the Sagittarius constellation, it is one of the most frigid and inhospitable worlds ever identified. This planet's characteristics are so alien and severe that it has earned the nickname Hoth Planet after the frozen world featured in the Star Wars saga. Its discovery was a significant milestone, shedding light on the diverse conditions under which planets can form and exist. This icy exile orbits a distant star in a system dramatically different from our own. OGL 2005 BLG 390LB was discovered in 2005 using gravitational microlensing, a technique that relies on the bending of light caused by the gravitational field of a massive object. This method is particularly effective for detecting planets far from their parent stars or in regions of space where traditional observational techniques struggle. The discovery was a collaboration between multiple astronomical teams, emphasizing the importance of international efforts in uncovering the universe's secrets. The defining characteristic of OGL 2005 BLG 390LB is its extreme cold. The planet's surface temperature is estimated to plunge to an unimaginable 370 degrees 223 degrees C. This makes it colder than any environment on Earth and one of the coldest exoplanets ever recorded. Such low temperatures are a result of its immense distance from its parent star. The planet orbits at a distance likely comparable to or greater than the orbit of Neptune in our solar system, leaving it bathed in perpetual darkness and isolated from any significant stellar warmth. OGL 2005 BLG 390LB is classified as a super-Earth with a mass approximately 5.5 times that of our planet. Despite this, its size and composition remain uncertain. Scientists believe that it is likely a rocky planet with a thin or negligible atmosphere. If this is the case, the lack of a substantial atmosphere would mean it has no insulation, allowing heat to escape freely into the void of space. This contributes to the extreme cold that defines its surface conditions. The planet's distant orbit and cold temperatures indicate that it resides far outside what scientists refer to as the habitable zone of its star system. The habitable zone is the region around a star where conditions might support liquid water, a key ingredient for life as we know it. On Ogle 2005 BLG 390LB, water would exist only as ice, permanently frozen and locked into its surface or subsurface layers. What makes Ogle 2005 BLG 390LB particularly fascinating is the insight it provides into planetary formation and survival. Most planets form within protoplanetary disks of gas and dust surrounding young stars. Ogle 2005 BLG 390LB likely formed in a similar manner, but its extreme distance from its host star raises questions about how planets can form and remain stable so far from the warmth and energy of their stellar parent. Its existence challenges some traditional models of planet formation, prompting scientists to reconsider the mechanisms by which planets can emerge and survive in such isolated conditions. The lack of light and heat means that Ogle 2005 BLG 390LB exists in near-permanent darkness. Its surface is likely barren and frozen solid, with no dynamic weather patterns or geological activity that could provide warmth or variety to its desolate landscape. This isolation and stillness are emblematic of many distant exoplanets, where the absence of energy creates environments that are stable but lifeless. Ogle 2005 BLG 390LB also serves as a glimpse into the outer edges of planetary possibilities. While it is not unique in being a cold, distant exoplanet, its extreme conditions make it an important subject of study. By understanding planets like Ogle 2005 BLG 390LB, scientists gain a broader understanding of the diversity of planetary systems and the physical limits of planetary environments. These studies contribute to a more complete picture of how planets, including those in the outer regions of their systems, might evolve over time. In summary, Ogle 2005 BLG 390LB is a world of extremes. Its frigid temperatures, vast distance from its host star, and apparent lack of atmospheric warmth make it an archetype of the harsh, frozen planets that exist throughout the cosmos. Though it may seem like an unremarkable, icy wasteland, it represents an important piece of the puzzle in understanding the vast diversity of planetary systems and the range of environments that can emerge in the universe. Its discovery through gravitational microlensing underscores the ingenuity of modern astronomy and our ever-expanding capacity to explore the most distant and desolate corners of space. Kepler-22b, located approximately 600 light-years from Earth, is one of the most intriguing and puzzling exoplanets ever discovered. Identified in 2011 by NASA's Kepler Space Telescope, this planet orbits a sun-like star within its habitable zone, the region where conditions might theoretically support liquid water and, by extension, life as we understand it. Yet the promise of habitability is overshadowed by the planet's formidable and alien nature, which presents a stark warning. Appearances can be deceiving. Kepler-22b is classified as a super-Earth or mini-Neptune due to its size, which is about 2.4 times the radius of Earth. While its location in the habitable zone initially sparked hopes of an Earth-like world, its immense dimensions raised doubts. A planet this large is unlikely to possess a solid, rocky surface similar to Earth's. Instead, it is probably enveloped in a thick, hydrogen-dominated atmosphere, making it a fundamentally different type of world. Such an atmosphere would generate extreme pressure and temperatures, effectively creating a hostile environment for any form of life we might recognize. The planet's structure is one of its most intriguing mysteries. Scientists hypothesize that Kepler-22b could have a rocky or icy core beneath layers of dense gas. However, the exact composition remains uncertain due to limitations in current observational technology. If the planet does have a solid surface, it lies buried under an atmosphere so thick that reaching it would be nearly impossible, even for the most resilient spacecraft. The pressure at the surface, if it exists, could rival or surpass that found in the deep interiors of gas giants like Neptune. Kepler-22b's atmosphere poses another challenge to habitability. A hydrogen-rich atmosphere would trap heat through an extreme greenhouse effect, potentially creating a sweltering environment far beyond what life could endure. Even if the planet's distance from its star allows for moderate surface temperatures, the crushing atmospheric pressure and lack of breathable air would render it uninhabitable by Earth's standards. Another possibility is that Kepler-22b might be an ocean world, with a global ocean hundreds or even thousands of kilometers deep. While the idea of an endless ocean may seem tantalizing, such a world would likely lack a solid surface for organisms to anchor to. Furthermore, the immense pressure at the bottom of such an ocean would preclude the existence of life as we know it. Without geological activity to cycle nutrients or provide energy sources like hydrothermal vents, the ocean could be biologically barren. Kepler-22b's distance from Earth complicates the search for definitive answers. At 600 light-years away, even our most advanced telescopes struggle to discern its precise characteristics. Scientists rely on indirect methods, such as measuring the dimming of its host star during transits, to infer its size and orbital details. Observations of the planet's atmosphere, crucial for understanding its potential for habitability, remain beyond the reach of current technology. Despite these challenges, Kepler-22b continues to captivate astronomers. Its discovery was a milestone in the search for Earth-like planets, highlighting the diversity of worlds in our galaxy. Kepler-22b reminds us that the concept of habitable zones is far more complex than originally thought. A planet's size, composition, and atmospheric conditions are just as important as its distance from its star in determining its suitability for life. Kepler-22b serves as a humbling reminder of the vast unknowns that still confront humanity in its exploration of the cosmos. While it lies in the Goldilocks zone, where conditions might seem just right for life, its alien nature warns us not to assume that habitability is a simple matter of temperature or distance. Instead, Kepler-22b represents the intricate interplay of forces that shape the universe's countless worlds. It is a planet of profound contradictions, inviting from afar, yet forbidding upon closer scrutiny. For now, Kepler-22b remains an enigmatic outpost in the cosmos, a testament to the complexity of the planets that lie beyond our solar system. WASP-12ab, a planet so extreme that it challenges our understanding of what worlds can endure, stands as a testament to the harsh and unforgiving nature of the cosmos. Situated approximately 1,400 light-years from Earth in the constellation Auriga, this gas giant is locked in a relentless struggle with its host star. Its unique characteristics make it one of the most horrifying planets discovered in our galaxy. This exoplanet orbits its star at a perilously close distance, completing a full revolution in just over 24 hours. Such proximity means WASP-12ab is tidally locked, with one hemisphere perpetually facing the star, while the other is shrouded in eternal darkness. This configuration creates a stark and horrifying dichotomy between the two sides of the planet. The day side, constantly exposed to the brutal onslaught of stellar radiation, is an inferno where temperatures soar above 4,000 degrees, 2,200 degrees. The heat is so intense that it strips molecules apart, turning the atmosphere into a chaotic mix of atomic components. The planet's atmosphere absorbs nearly 94% of the light from its star, a level of absorption so high that it renders the day side a near pitch-black void. This phenomenon is highly unusual for a gas giant, which typically reflects a significant portion of incoming light. Instead, WASP-12ab's day side is akin to an all-consuming abyss, where light seems to vanish upon arrival. In contrast, the night side of WASP-12ab exists in perpetual darkness, shielded from the searing heat of its star. However, this darkness is far from serene. The temperatures drop drastically, creating an environment that is inhospitable in its frigid stillness. The dramatic temperature difference between the two hemispheres drives extreme winds, which rage across the planet at speeds exceeding thousands of miles per hour. These winds attempt to redistribute heat, but the process is inefficient due to the planet's atmospheric conditions. The gravitational pull of WASP-12ab's host star is so immense that it distorts the planet's shape, stretching it into an elongated oval form rather than the usual spherical shape associated with planets. This gravitational warping is a direct result of the intense tidal forces exerted by the star, further exacerbating the extreme conditions on the planet. Adding to its horrors, WASP-12ab is slowly being devoured by its own star. The intense gravitational interactions are siphoning material from the planet's outer layers, a process known as Roche lobe overflow. As a result, WASP-12ab is losing mass at an alarming rate, with its atmosphere bleeding into space and forming a stream of gas that spirals into the host star. Astronomers estimate that this process will ultimately lead to the planet's complete destruction within the next 10 million years, a mere blink of an eye on cosmic timescales. The atmospheric composition of WASP-12ab also sets it apart from more familiar planets. Observations indicate an unusual abundance of heavy elements, including carbon. This high carbon-to-oxygen ratio suggests that the planet might harbor exotic chemistry, potentially leading to the formation of compounds like carbon monoxide and methane in its atmosphere. Such conditions would be unthinkable for any form of life as we know it. The study of WASP-12ab has provided scientists with invaluable insights into the behavior of planets under extreme conditions. Its warped shape, superheated dayside, and evaporating atmosphere make it a natural laboratory for understanding tidal forces, atmospheric dynamics, and the interactions between stars and their close-in planets. These observations challenge theoretical models and offer a glimpse into the fates of other similarly situated exoplanets. WASP-12ab stands as a stark reminder of the violent and volatile nature of our universe. It is a world where light and dark exist in perpetual conflict, where intense heat and freezing cold are separated by a narrow boundary of ferocious winds, and where the very fabric of the planet is being torn apart by the inexorable pull of its star. It is a testament to the extremes that planetary systems can reach, and a vivid illustration of the countless ways in which the universe defies human imagination. GJ-504b, often referred to as the Pink Nightmare, is one of the most visually striking and scientifically intriguing exoplanets discovered to date. Located approximately 57 light-years from Earth in the constellation Virgo, this young gas giant is unlike anything in our solar system. Its magenta glow, caused by heat left over from its formation, sets it apart as a hauntingly beautiful yet profoundly inhospitable world. At the heart of GJ-504b's mystique is its vibrant coloration. The planet's magenta hue arises from the intense thermal radiation emitted by its still-cooling atmosphere. When GJ-504b formed, the colossal energy of its birth generated extreme temperatures, and while it has cooled over millions of years, the residual heat remains substantial. This heat interacts with its thick atmospheric composition to produce the eerie pink glow that astronomers observe. GJ-504b's atmosphere is a complex and hostile mix of gases. The dominant elements include hydrogen and helium, common in gas giants, but it is the additional presence of methane and other volatile compounds that truly define its character. Methane absorbs light at specific wavelengths, enhancing the magenta appearance, but it also contributes to an environment that is chemically unwelcoming. These volatile compounds form dense clouds that perpetuate the planet's extreme weather and harsh atmospheric conditions. Temperatures on GJ-504b exceed 1,000 degrees Fahrenheit, over 500 degrees Celsius, creating a searing environment that prevents the possibility of life as we know it. The high temperature, combined with the planet's dense atmosphere, results in crushing pressures that would obliterate any terrestrial structure attempting to endure them. This is a world shaped by violence and heat, a stark reminder of the raw forces at play in the universe. Adding to its strangeness is the fact that GJ-504b is relatively young in cosmic terms. At approximately 160 million years old, this exoplanet is still in the early stages of its evolutionary journey. For comparison, Earth is more than 4.5 billion years old. The youth of GJ-504b means it retains much of the heat from its formation, which not only gives it its striking color, but also keeps its atmospheric dynamics in a state of chaos. Convection currents and high-energy interactions in its atmosphere likely produce storms of unimaginable ferocity, far beyond anything seen on Jupiter or Saturn. GJ504b also offers scientists a fascinating glimpse into the formation and evolution of gas giants. As a planet outside our solar system, it challenges many of our assumptions about how planets develop. One of its unusual features is its orbital distance from its parent star. GJ504b orbits much farther away than the gas giants in our solar system. This wide separation makes its formation something of a puzzle, as current models of planetary formation struggle to explain how such massive worlds form at such great distances. The discovery of GJ504b has pushed scientists to reconsider and refine their theories. Another significant aspect of GJ504b is its mass, which is estimated to be about 4 times that of Jupiter. Despite its large mass, its low density indicates it is primarily composed of gas with little to no solid core. This composition aligns it with other gas giants, but underscores just how extreme and varied these planets can be. It is a reminder that, in space, no two planets are truly alike. For astronomers, the discovery and study of GJ504b have been a milestone. Its unusual characteristics make it an ideal subject for research into exoplanet atmospheres and the physical processes that govern young planetary systems. The vivid magenta glow has also allowed scientists to test and refine imaging techniques, as GJ504b is one of the relatively few exoplanets that can be observed directly using high-powered telescopes. In summary, GJ504b, the Pink Nightmare, stands as a testament to the diversity and extremes of planetary systems in our universe. Its hauntingly beautiful appearance belies the dangerous and uninhabitable environment it hosts. The thick, methane-laden atmosphere, scorching temperatures, and volatile chemical composition make it a world of extremes, illustrating the vast range of conditions that exist beyond Earth. While we may never visit GJ504b, its discovery has deepened our understanding of the cosmos and continues to inspire wonder and curiosity about the universe's boundless possibilities. HED 80606b is a planet that defies our expectations of stability and order in the cosmos. This gas giant, located approximately 190 light-years from Earth in the constellation Ursa Major, is a place of extraordinary extremes and violent transformations. Unlike the nearly circular orbits of most planets in our solar system, HD 80606b follows an exceptionally eccentric orbit, more like that of a comet than a typical planet. This path takes it on a dramatic journey around its parent star, plunging it into scorching heat and pulling it back into relative cold with every cycle. The orbit of HD 80606b is a scientific anomaly. At its farthest point, the planet is a considerable distance from its star, experiencing relatively mild temperatures for a gas giant. However, as it swings closer to its host star, it dives into an intense gravitational and thermal tug-of-war. This close approach, known as periastron, occurs once every 111 Earth days. During this period, the planet is subjected to an extraordinary increase in stellar radiation, causing temperatures to surge from around 900 527 degrees to nearly 2,000 1,093 degrees in a matter of hours. This extreme thermal shock is unparalleled in planetary science, representing one of the most dramatic examples of a climate shift ever observed. The sudden rise in temperature triggers catastrophic changes in HD 80606b's atmosphere. Gas giants like this are characterized by thick layers of hydrogen, helium, and other gases. But the rapid heating causes these layers to undergo violent transformations. Atmospheric layers that were stable during the planet's cooler phases are disrupted, collapsing and reforming in a chaotic dance. This atmospheric turbulence generates massive storms and high-speed winds that sweep across the planet at thousands of miles per hour. The planet essentially undergoes a form of atmospheric reset during every close pass to its star. This phenomenon has led scientists to describe HD 80606b as having wild seasons. Unlike Earth, where seasons change gradually over months, the transitions on HD 80606b are sudden and extreme. The concept of summer on this planet is marked by a fiery blast of energy that lasts only a few hours but leaves lasting impacts on its climate and atmospheric dynamics. During this period, gases in the atmosphere expand rapidly, creating shock waves and temperature gradients that ripple across the planet's surface. As the planet moves away from its star, the cooling process is just as rapid, causing the atmosphere to contract and stabilize once more. The planet's eccentric orbit is believed to be the result of gravitational interactions with a companion star in the HD 80606 system. This secondary star likely played a role in shaping the unusual trajectory of HD 80606b, pulling it into a stretched-out orbit over millions of years. Such interactions are not uncommon in binary star systems, but the extreme nature of this planet's orbit makes it a rare and valuable case for study. It provides insights into the chaotic forces that can shape planetary systems and the diverse environments that exist beyond our solar system. One of the most fascinating aspects of HD 80606b is its ability to retain an atmosphere despite the extreme conditions it endures. The intense heating during periastron would strip away the atmosphere of a less massive planet, but HD 80606b's immense gravity helps it hold on to its gaseous envelope. This resilience offers a unique opportunity for astronomers to study the composition and behavior of an atmosphere under extreme stress. Observations using telescopes, such as the Spitzer Space Telescope, have revealed dramatic changes in the planet's brightness during its close approaches, providing valuable data on how its atmosphere responds to rapid heating. HD 80606b is more than just a scientific curiosity. It challenges our understanding of planetary physics and climate dynamics. It serves as a natural laboratory for studying the effects of extreme temperature variations, high-energy radiation, and gravitational interactions on planetary atmospheres. The knowledge gained from studying such worlds could help us better understand the diversity of exoplanets and the potential for life in extreme environments. In conclusion, HD 80606b stands as a testament to the incredible variety of worlds that exist in our universe. Its wild seasons, marked by rapid and extreme temperature swings, make it one of the most extraordinary planets ever discovered. While it is a place of chaos and extremes, it offers a glimpse into the complex and dynamic processes that govern planets across the cosmos.